Good afternoon, everyone. My name is Davit Mkrtchyan, and my capstone project called Injection Mold Design for a Component Storage Box. The project was supervised by Professor Sarkis. So let's quickly look at the agenda of today's presentation. Firstly, I will introduce the molding process overall for you to make an starting imagination about the molding process. Then I will talk about the inspirations, the goals I have about this design and analysis, the actual design process, the analysis, the results of the analysis, and the challenges I've met. So let's look this video, and I will give you a small injection mold part, which after the pump will become a small bottle, 0.5 liters bottle. So, sorry. So the first part of injection molding. So the first starting part of the injection molding was the filling the granules, the plastic granules. Then, with the help of these heating elements, these plastic granules were melted. After getting melted, with this shaft, with the screw and the non-returning shaft, they are injected into the part where where the final part will be melted. Then ejected. And repeatedly all this process was done to create this kind of molded parts. So the inspiration of my project was the collaboration with a local Armenian company, which is working with mechatronic systems, and logically they are also working with PCBs and designing PCBs. So they've got an idea to create a storage box for electronic parts like this one with the tape to create the storage box to optimize the working process. So how it works? The design engineers, they are creating the PCBs, and when they need to already assemble all these design parts, they need to find the corresponding parts. So with the help of this box, they can find easily their components from the warehouse, and this box is connected to a software which traces to the corresponding parts. It is actually out of my scope, but I've just worked purely with the mechanical part of the project. So I think the most important part of the collaboration with the company is to meet their goals they have set from the start. I've mentioned here 4 main goals: the scale production, to increase the manufacturing capacity and to meet higher demand more efficiently, to reduce the unit costs, because we all know that the 3D printing is very time consuming in comparison with molding, and also is expensive. Also, they want to enhance durability and the finish of their models, which we cannot do with the 3D printers as good as we can with the injection molding, and optimize material usage and be able to change some features, the shapes, the design of the parts easily with some inserts on the mold. The first part of the analysis is material selection. This is very crucial for the project because we need something which is very durable, uh, easy to easy to be molded, easy to be melted, and shaped in a be shaped in a uh, mold I've created. So, with the help of this company, with the help of their engineers, and also my research, we have chosen to use an ABS as a main material for our molding because it is very durable in some prototype tries. They concluded that ABS have a good durability and finish, surface finish. So uh, we try to create the mold to use with an ABS plastic. The next analysis part is the field analysis, uh, which uh, which is dedicated to understand how the filling process was done. Uh, this analysis was done by this software called SolidWorks, and after some slides, I will show you the defects which we can get because of not doing this analysis. And in the result, we see that the filling time is approximately 2 seconds. Uh, you can imagine, mm, as you can imagine, the uh, process of 3D printing of this part actually takes 2 to 3 hours for a medium quality. So the next phase is draft analysis. Here you can see with these pictures that some models need to be drafted. The angle must be given to the surface because uh, for the standard molding process, for the ejection process, we need to give some angle to the surfaces because we will not be able just to pull out the model out of the form if we will not do the drafting analysis and will not give angles to the surfaces. So here you can see the draft analysis uh, with and without drafted angles. Here I've tried to design the upper part, this part of the mold. And on the left picture, the yellow ones are not drafted. On the right one, they're drafted. And as you can see, it is given 1.5 degree of draft angle. It is also very specific for different projects, for different models, and it is connected with their specific designs. And also, the part of the design is the modeling of the inserts. As my model is not quite easy one, I need to design some inserts for this model. So in total, I have 3 inserts. And two main parts, the core and cavity. All this analysis part was done for not meeting these defects, and these are not the only ones, but the most common ones: the sink marks, the flow lines, short shots, and warping. As you can see, the causes and the solutions are probably the same in most of the cases, because when we are working with a plastic, It is, and with the plastic and the injection of the plastic, it is very important to consider the facts like injection speed, the pressure of the molding, the temperature, and factors like that. I want to show you the results that I've got after the analysis. So, as we want to get a scale production, we can compare 3D printing and injection molding. As I've said, for the standard quality, you can see that we need to spend 4 to 6 hours to print this part. But with injection molding, we can do that in maximum 40 seconds. And in the case of multi-cavity molds, we can do that much faster. Also, I want to mention that I get a good result for the reduced unit cost. As you can see, for the 3D printing, the cost of one unit is it varies from $3.5 to $5.5. And in the case of injection molding, the molded part, it will cost $0.9 to $1.7. Lastly, I want to discuss the challenges that I've met. So here is only the main one. Actually, the challenges are quite a lot, but here is only one challenge, and the main challenge that I've met. And it was the redesign of the prototypes. As you can see, the first prototype is completely different, and it doesn't look like the last one and the final design that we have now. So it is very challenging to repeat the same cycle. As I've already mentioned, the material selection, defining injection point, the fill analysis, draft analysis, and design of the inserts. That's all. Thank you, everyone, for your attention.
Question? Yeah. You said that it can't be 90 degrees or it won't come out of the mold. Did I understand that correctly?
Yeah. It
so it like sort of drops? Is that how it comes out?
In the case it will give a 90-degree angle. We have two scenarios. Or the first scenario, we will get one of these defects, and the worst scenario is that we will not be able to pull out the form, pull out the model out of the form.
Can you go to the next before the thank you? Can you go to that slide?
This one?
Yeah. These challenges, which one did you actually kind of concentrate on in your work?
I think the draft angles, because I can show you on the model. As you can see, there are many directions that I need to draft. That I need to draft, I need to create angles, drafted angles. So I think it is the most challenging part to calculate it effectively and design it somehow to get a final version of the model according to the needs of the company, and at the same time to be able to connect these angles with each other.
I mean, you kind of mentioned in passing that this is a pretty tough problem because there's a lot of things that affect how we actually inject and where we inject the material.
Yeah.
So this is a very highly non-Newtonian kind of flow. It is not a typical type of flow that you have here.
This one?
When you're actually molding when you're actually putting the material into your mold to create your part. So my question is, did you do any analysis, or for example, fill analysis that you write there? Did you actually take a look at what some of the issues can be? Because the viscosity of the material that you're using is highly dependent on the shear that it feels, the temperature, the cooling, and so on and so forth. So where it goes, how it goes, depends on all of that, and of course the injection pressure. So did you do any type of back of the envelope analysis for that, or you just concentrated on these angles and so on?
No, of course I did. As I've mentioned here, I did the field analysis, and I did the analysis of defining the injection point. As you have mentioned, it is very important to define where to set the point for the injection, because, for example, if I will set it in a different place, maybe the flow will be completely different, and also the temperature and the pressure acts on this process. So yeah.
This was done in SolidWorks?
Yeah.
So this was basically the CFD module inside SolidWorks that did this?
There is a plastics module called plastics analysis. So I've used this software to do it. Yes, please.
If I could just ask more, when you make, let's say you make 189, the other one could be 91, or it can't be more than 90. So if you want to have this thing nice and straight, how do you?
You can have this thing nice and.
So those really, like, none of this stuff is really 90 degrees, like this plastic things we have, or are they close?
No, most of the angles are not 90 degree. Only the outer angles, these outer angles, because this distance is not too much, and the ejection process and opening process could be done with this kind of distance. But if we work with the bigger projects, bigger components and bigger models, we also will need to draft these angles also. But the inner angles are drafted. They're not 19-degree angles.
Because it's not sticking, is that why? Because it doesn't stick to the outside?
Yeah.
Oh, okay.
Questions? No?
When this is invented, you know?
Invented?
Yes.
This was not invented yet. The molding, you mean?
Injection molding.
Injection molding? I assume maybe during the 20th century, because we have a site visit with my supervisor, and I've seen many of machinery, old machinery, which are 50, 60 years old. So I assume maybe 20th century, yeah.
And why you decided to compare it with the 3D printing?
Because this company used to do this, used to create these parts with 3D printing. That's why I'm comparing these two.
Thank you.
Thank you, too.
Since I have one more question, just interesting about that story. So when you go into, so how many samples you need that company needs for such a thing? How many samples they need?
How many samples?
Yeah.
I didn't
Of
get
this
this.
storage. You call it storage, yes? The storage for some.
Yeah. For in the warehouse, you mean? In their warehouse? I don't know. I don't have access to this kind of information.
Do you know what is the cost for creating the form? For
The
doing
form?
the injection molding?
Yeah, I showed it here.
Mm-hmm. Yeah, maybe I. No, there is not such an
No,
information.
that's the production cost for
Yeah.
one piece.
That showed negative mold.
To negative
That
mold?
should be
The
prepared.
cost, yeah, the cost.
Oh,
of
for the form?
actual cost, yeah, cost form, yeah.
It is very expensive. That's why I've 3D printed it all. So maybe $50,000 to $60,000.